Hello friends, my name is Mr. Dhawale from Rao Bahadur Narayan Rao Borao K College, Sri Rampur. Today we discuss about reactions involving cyclohexyl ring system. In cyclohexyl ring system, there are so many reactions. Okay, in few last lectures we take some examples. In today's lecture we cover more reactions regarding this topic. Okay, so today first we take an example of cyclohexyl ring with substitution. In that, first we take one question regarding this. Under the point sterically hindered and assisted reactions. Sterically hindered and assisted reactions. Okay, in that we take one problem regarding this. In axial and equatorial substituent, suppose we take an acid or ester. Okay, cis and trans isomer of suppose we take here this example. Suppose this is a cis isomer, and in this case here suppose this is carbonyl, and here this is OR, means this substituent is ester, and this is tertiary butyl group. Both groups are bulkier, but in cis cyclohexane, substituted cyclohexane or cis conformation, there is presence of one substituent at axial position. So this ester group is present at axial position, and in trans isomer there is two conformations. In that case, trans equatorial and trans diaxial. Okay, so here we take a stable structure trans equatorial, and here this C structure is equatorial axial. So we take this example in sterically hindered reactions or sterically hindered and assisted reactions. Okay, in this case, suppose we carried out saponification. Here OH minus. Okay, at that time this OH minus, which acts as a nucleophile when attack on the carbonyl carbon atom of an ester, at that time we get a bulk. Okay, we get bulk here. Suppose this nucleophile is attacked on this carbonyl carbon, this pi bond which was broken, and we get here one intermediate having O minus, here we write OR, and here we write OH, which acts as a nucleophile, and this intermediate is a product of the first step. Okay, so in this intermediate there is presence of huge bulk. Okay, as compared to starting material, here this is somewhat less bulkier, somewhat smaller than that of this intermediate step. Okay, at that time bulk accommodated at the axial position, and axial position is somewhat or highly unstable state. Okay, so the intermediate is not present in this state for a long time. Okay, then after this it will next converted into the corresponding acid. Okay, now this negative charge can form double bond or can form carbonyl group, and this OR alkoxy group will removed from this intermediate, and we write here OR minus, and finally we get here product which is acid. Okay, now we compare this and this one. Suppose this is ester and this is substituted acid. From these two, this is somewhat stable. Why? Because less bulkier substituent as compared to this ester, so that when we go for this type of reactions, first step is somewhat slower, but second step is more faster. Why? Because the intermediate is highly unstable. This intermediate is highly unstable, so that this reaction is fast, so fast, but first step is slow. First step is slower step. Okay, then if we go for second, we go for trans isomer. At that time, in same reaction is carried out, OH minus will attack on carbonyl carbon. After that, we get here a intermediate O minus, here we write OH and here OR. Okay, thus intermediate is bulkier. Okay, this intermediate is somewhat more bulkier, but that bulk is accommodated at the equatorial position, so that there is no any effect on the stability of this molecule. Okay, so you remember this is the bulk. Okay, as like in first reaction, the bulk is present at the axial position, so that it will much effect on the stability of this molecule. Okay, but when we go for trans isomer, at that time bulk is formed, but that bulk is accommodated at the equatorial position out of the plane, so that we say here there is no any effect, or if the effect is done, but that effect is very small on the stability of the molecule, so that the reaction contain first step, and the first step is somewhat slower or somewhat faster. Okay, here the first step is slower, but here the first step is fast, and second step, which contain the loss of alkoxy group, is carried out, and we get a final product as an acid, substituted acid, which is also present at the equatorial position. Okay, trans acid we get here, okay, but in this reaction this is somewhat slower or normal rate is there in both cases. So that first you ask one question, we write here a question regarding this, the rate of the cis isomer is higher than that of trans isomer, okay. So here we write slow, okay. When we go for or when we focus on this step, okay, in this step the step is much faster and very fast. Why? Because bulk accommodated at the axial position. And in this step here, in second example, second step contain bulk is at equatorial, so that the step is slower. And from the overall explanation we can conclude that when bulk is more at axial position, the rate of reaction is faster, and when the bulk is at equatorial position, at that time the rate of reaction is slower. So the question is, why the cis isomer can react faster than that of trans isomer or trans conformer, okay. So you explain as like this, okay. Then we go for sterically assisted reaction, okay. Then next example we carry out. Next point, we take another example, trans 4 tertiary butyl cyclohexyl para nitrobenzoate is saponified 2.5 times faster than the corresponding cis isomer, but trans ethyl 4 tertiary butyl cyclohexane carboxylate is saponified 20 times more faster than the corresponding cis isomer. Here we carried out two different examples, okay, but the theme is same, okay. Now we go for first example, 4 tertiary butyl cyclohexyl para nitrobenzoate, okay. So here we try to write its a structure, okay, and here the substituents are, we write like this. Suppose this is oxygen and another substituent is carbonyl, suppose this is phenyl ring with NO2, okay, and another substituent is here, okay. We try to draw all the structures, NO2, okay. This is trans isomer and this one is cis isomer, okay. Both this isomer, and rate of this reaction is not much differ between cis and trans, okay. The difference between the rate, suppose we say here cis isomer is 2.5 times more faster than trans isomer, okay. So here we write 2.5 times, okay, and this is the difference between these two, okay. Means what? This cis isomer is somewhat 2.5 times more faster than trans isomer, okay. So what is the reason? So as we see in last example, when bulk is more at axial position, the rate of reaction is faster, and when bulk is at equatorial, at that time rate is slower. Okay, by using such concept, also we can apply that concept for this example. At that time we see here bulk is not totally accommodate at the axial position here. Okay, suppose the reaction is carried out. Suppose your nucleophile or saponification reaction, at that time nucleophile hydroxyl group will attack on this carbonyl carbon, and we have the intermediate like this one. Okay, this is chair conformation, this oxygen, this here we get O minus, here we write OH, and here I write pH NO2. I write this in short, you understood very well. Okay, now you see here the bulk accommodated at the axial position is not much axial or not exactly at the axial position. Why? Because the bulk and the cyclohexyl ring is joined by the oxygen atom. Okay, and this bulkier group is not exactly present on the axial position, so that it does not differ or does not affect much on this cyclohexyl ring or stability of the cyclohexyl ring. And here in second example also bulk accommodated, I write here, I am trying to show you the bulk which is at the equatorial position. So this equatorial position, bulk accommodated at equatorial position and bulk accommodated at the axial position, there is no much difference in the stability of the cyclohexyl ring. Why? Because this both bulkier group and cyclohexyl ring are somewhat away from each other, so that they can't differ, somewhat major difference is not seen in stability of this cyclohexyl ring. Okay, so that the rate of the both cis and trans isomer doesn't differ in much amount. Okay, here is only 2.5 times more faster cis isomer as compared to trans. But when we go for another example, here another example is trans ethyl 4 tertiary butyl cyclohexane is more faster. Okay, so how its rate is greater? Okay, here this is and this one is trans. Okay, and in this example trans ethyl 4 tertiary butyl cyclohexane, trans ethyl 4 tertiary butyl cyclohexane. Suppose this is ethyl group and this is cyclohexane with equatorial substituent of tertiary butyl. Then here we write this is oxygen C2H5 benzoate. Okay, this is benzoate, trans ethyl 4 tertiary butyl cyclohexyl benzoate. Okay, so that we write or we start writing name with ethyl group. Okay, so this is the trans isomer. Here we see the trans isomer is 20 times more faster than that of cis isomer, and here this trans isomer is only 2.5 times more faster than the cis isomer. Okay, so Here we can explain this. Okay, now here we write this is trans, but this is carbonyl, this is oxygen, and this is C2H5. Okay, here this is cis isomer. Okay, this cis and this one is the trans isomer, and you also see these two isomers. What is the difference? What is the major difference between these two examples? In case of trans isomer, this is also a trans and this one is also trans isomer. Here tertiary butyl group in both cases are same, but here we see carbonyl group is directly attached to the cyclohexyl ring, and here this carbonyl group is not directly attached to the cyclohexyl ring. Okay, this is the reaction center. This is reaction center. So bulk is formed in intermediate step at this carbon atom, so that this is much importance for the stability of the cyclohexyl ring, and the carbonyl group is somewhat away or differentiate by this oxygen, so that it doesn't differ in the reaction rate in much greater way. And in this case here this carbonyl group is directly attached to the cyclohexyl ring, so that bulk accommodated at this stage is much affect on the stability of the molecule, so that the reaction rate difference in these two cases is much greater. This is 20 times more faster. The rate of reaction or difference in the rate of reaction is 20 times. Okay, in trans isomer is much greater, faster in this case, and here in cis isomer there is no reaction is faster and difference is about 20 times, but in this case here very small difference is there and the difference is only 2.5 times. Okay, so that from this overall explanation we can say that so many reactions are notified. In that case steric hindrance is also favorable for the rate of reaction. Okay, and that's why we call this is sterically hindered and assisted reactions. Okay, thank you.